Greetings and a very good day to everyone. We are from Group 3. Our presentation topic today for electromagnetic field theory course is about polarization in dielectric. So here is about our group, and I will give a simple introduction to dielectric materials. A dielectric material can be defined as a type of electrical insulator or poor conductor that supports electrostatic fields effectively. So basically, a dielectric has high specific resistance, a low temperature coefficient of resistance, and a higher ability to retain the electrical charges.
Now let's take a look at the theoretical analysis of polarization in dielectrics that consists of dipole moment, bound charge density, and effect of polarization on fields. In the initial period of an atom or a molecule, it's usually neutral because of the equal number of positive and negative charges in it. When electric field E is applied, the positive charge is displayed from the equilibrium position in the direction of E by the force F equals to QE, while the negative charge is displayed in the opposite direction by the same force. And because of this distortion of charges, the dielectric is polarized, creating a dipole moment P equals to QD, where the d is the distance between the distorted negative charge and the positive charge. Now, through this explanation, we get the polarization P is defined as the dipole moment per unit volume as per the given formula here. Now, when polarization occurs, an equivalent volume charge density is formed throughout the dielectric, while an equivalent surface charge density is formed over the surface of the dielectric. We denote them as surface charge density, that is rho p equals to p into n, and volume charge density, that is rho b equals to negative delta into p. We now consider the case in which dielectric region contains free charge. If rho v is the volume density of free charge, then the total charge density rho t is given as rho v plus rho pv equals to del of epsilon naught and E. Hence, by doing the derivatives, we get that rho v is equals to delta d and d is equals to epsilon E plus p. In the polarized field, its effect is according to the vector of electric flux density.
One of the implications of polarization in dielectric is electret. The word electret itself was to describe dielectric materials with quasi-permanent space charges or dipoles. To this point, polymer electrets belong to the dielectric materials, which exhibit a dipolar polarization or quasi-permanent electrical charges. It is usually the voided charge polymer film that is prepared in virtue of the electric charging process. When applying a high electric field, those separated charges with opposite symbols will be trapped on the internal surface of voids, which brings about electric dipoles. Mechanical pressures will then contribute a non-uniform deformation in the charge film, macroscopically leading to electric dipole moments and piezoelectric effect. More importantly, polymer electrets have shown advantages such as cost-effectiveness in preparation and low acoustic impedance matched to water and the human body, supporting their further potential applications in flexible sensors.
Another application for polarization in dielectric is the capacitor. In a parallel capacitor plate, there is a dielectric in between them. This dielectric is inserted to increase the capacitance of the capacitor as it can be easily polarized. Assuming that the capacitor is connected to a full circuit, when voltage is applied, an external field is present in the dielectric, where the direction of the field is from the plate connected to the positive of the power supply to the other plate of the capacitor. When there is the existence of an external electric field, the dipole moment and polarization vector will appear. The positive and negative bond surface charge will exist on the plates, while the bond volume charge will be in the dielectric. These dielectrics, which form the bound surface charge and bound volume charge, serve as keeping the plates in contact and increasing the effectiveness of capacitance by reducing the electric field strength to get the same amount of charge with a lower voltage.
To sum up everything just now, we can conclude that dielectric materials can be polarized easily when an electric field is applied to it. And there are some theories that relate to dielectric materials such as dipole moment, bound charge density, and its polarization effect on electric fields. And besides that, electrets and capacitors are the common application for polarization in dielectric. And that's all about for our group, and thank you for your listening.